Hello everyone, if you're new here, this is Chandan and you are watching the learning field. So this is the lecture I think 5. Okay, so this is the lecture 5 for the class of LPP. Okay, and this session is very helpful for, we all know that, for GATE, for CSIR NET, for any state level set examination set, and any other different type of exams of LPP syllabus. Okay, so in this lecture we will cover the simplex method and based some examples and sub theorem based on simplex method. Okay, and one more thing is that in this lecture we will cover the fundamental theorem of LPP. Okay, so before starting, I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and subscribe the channel. Okay, so we first read what is the fundamental theorem of LPP. Okay, and one more thing is that there are already 4 lectures we have covered. The link will be in the description and also here in the I tab. Okay, so you can watch the previous lecture for your reference or for your help. Okay, so what is fundamental theorem of linear programming? Okay, so if the LPP optimize z equal to c transpose x subject to ax equal to b or x greater equal to 0, A is an m by n matrix of rank m has an optimal solution, then there exists at least one BFS, that is basic feasible solution, which is optimal. Okay, so in the last class or in the last video we already covered a problem which is based on this theorem. Okay, that is if there is optimization problem with subject to the ax equal to b, then there must exist at least one basic feasible solution. Okay, this is the fundamental theorem of LPP. Now it comes to another important theorem, which is Minimax Theorem. So if the objective theorem z equal to c transpose x attains its minimum value at x0, then the function z star equal to minus z equal to minus of c transpose x attains its maximum value at x0, and maximum of z star this is equal to minimum of z. Okay, and maximum of minus z equal to minus of minimum of z. Okay, so this is the known as Minimax theorem. Okay, you read it very clearly and very properly because this is a very important theorem in LPP. Okay, we need this theorem to solve the various types of problems. Okay, so this is the theorem. Now we comes to the simplex method, which is our very important topic, and in this video this lecture is basically for the simplex method. Okay, so we directly go to the simplex table. Okay, we don't go to the more theory part, so we directly go to the simplex table. Okay, so this is like a simplex table. Okay, so what is the topics? This is what is the components, okay, of the table. So this is suppose maximum of suppose optimize z equal to c transpose x. Okay, and ax is equal to b. So this b vector is this b vector column vector. Okay, and now and this matrix A matrix, this is suppose m by n matrix. This is called the matrix with m by n order, and this is the matrix. Okay, component of the matrix A is here. Okay, so this is the structure, and b vector is this vector b, this one, and we covered a vector, and z means, okay, what z means cost. Okay, so cost means this is the cost vector c1 c2 up to cn. Okay, so this is the cost vector, that is z. Now this x vector is up to m, so this is the vectors, okay, which are we need to find the value, and this is the basis corresponding to this matrix, these basis vectors and these vectors, and these are the costs corresponding to the vectors which are in the basis. Okay, so this is the case of this is the components of the simplex table. Okay, and there is another column which is the minimum of x bi by y bi. This is we have to calculate this thing for the calculating the outgoing vector and incoming vector. Okay, so we just hold this thing for now. Now we discuss this thing later. Okay, so and another one thing is that zj minus cj. These are the zj minus cj, that is delta 1, delta 2, and delta n up to. Okay, so how to find this delta j? This and this multiplying by this and this quantity, sum of this, we multiply these quantities and sum, that is what? That is cb1 into y1. So cb1 into y1 plus cb2 into y2 plus c dot 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 plus c bm y11, sorry, y11, y21, cbm into this term ym1 this minus c1, this is equal to delta 1. Okay, so this is the delta 1 and delta 2, delta 3, delta 1, so on. Okay, this into this plus this into this plus this quantity into this quantity minus this quantity gives the delta. Okay, in these lectures we take this convention. Okay, you will get another convention in different types of books. Okay, but we use here this convention. Okay, and based on this convention we here take the theorems or discuss the theorems. Okay, so what is the optimality condition for the case? So there is a theorem, a sufficient condition for the basis of feasible solution xb 2 and LPP maximize z equal to c transpose x subject to ax equal to b here, and we just take here the equality, and we are not introducing the slack or surplus variable in the theorems. Okay, in the latter we introduce the slack variable and surplus variables. Okay, so this theorem based on just equality type of constant. Okay, so to be the optimal is that jj minus cj greater or equal to 0. So this is the optimality condition. We have to find the optimality condition and we have to calculate the tables, or we have to find the number of iterations for to find this. Okay, to satisfying this optimality condition. Okay, for all the columns vectors a j of a. Okay, so jj minus cj for all j if greater or equal to 0, then we say that the LPP satisfies the optimality condition, and the vectors which are present in the basis we call the optimal solution of those vectors or the variables. Okay, based on the variables. So this is the optimality condition. Now the basic simplex algorithm. What is the basic simplex algorithm? Okay, so see what do we mean, or what work we have to do in the simplex algorithm. This is an summary type. Okay, you can say it. So see, start with the BFS, that is the basic feasible solution, which is called the IBFS. Okay, so first we have to choose an IBFS. How can we choose IBFS? We discuss this later. Okay, some test of optimality and test the optimality condition, that is Zj minus Cj either greater or equal to 0. If optimality condition satisfies, that is Zj minus Cj greater or equal to 0, the optimal the algorithm terminates, that is the method terminates or the method is khatam. यहाँ पर खत्म हो गया. ठीक है method. Otherwise find the another BFS by departing a vector from the basis and introducing a new vector in it, which will improve the objective function. And how to choose the introducing vector and the departing vector we just discuss it later. Okay, the optimality of new BFS is tested again. The entire process is repeated until the optimal BFS is found. Okay, this is the summary of an simplex algorithm. Since every time a new basic feasible solution improved, the objective function and the set of BFSs, that is basic feasible solutions, are finite, it follows that the algorithm will terminate a finite number of iterations. Okay, so this ensures that the iterations terminates after a finite number of times must terminate. Okay, this is not the infinite iteration. Okay, this is the finite iteration. Okay, so this is the summary of basic simplex algorithm. Okay, now we comes to the case of unbounded solution. What is the case of unbounded solution? So there is a theorem, LPP maximizing z equal to c transpose x subject to x equal to b, x greater or equal to 0 will have no finite optimal solution if there exists at least one column vector aj corresponding to the non-basic variables aj such that xj such that zj minus cj less than 0 and yij is less equal to 0 for all I. What is basic variable and what is non-basic variable, we discussed this thing in the previous lectures. Okay, so you can, if you are not know that what is basic variable, what is non-basic variable, then you can attend the previous lectures of LPP. Okay, to understand this thing, because this basic variable, non-basic variable, understanding of these terms are very important. Okay, so this is the theorem, that is in case one zj minus cj less than 0 for any of one of non-basic variable, then we must say that, and yij less equal to 0 for all I, then we must say that the LPP has what? No feasible solution, or here is the no feasible solution. Okay, so this is no finite optimal solution. So this is the case, and let us take an example depending on that theorem. So suppose maxima is z equal to 2x1 plus x2 plus 2x3 plus 9x4 subjects to there are two constraints and xi greater than equal to 0 for all I. Okay, so see, so I just said that how we choose the initial basic feasible solution. First we have to form a basis, form a unit vector. Okay, so see, if we write this inequalities in this table, okay, so we get 1 0 0 2. These are the coefficient of for the first constants of x1 x2 x3 and x4, and write the second constant, we get 0 1 minus 1 and 1. Okay, so 0 1 minus 1 and 1. Okay, so see, a1 and a2 form a basis. Okay, that means we take the what here we take a1 and a2 as these two terms and these two values, that is 2 and 3 corresponding to a1 and a2, the remaining are zeros as an initial basic feasible solutions. Okay, this is clear, I think. Which form the basis, we take corresponding these quantities to form to take the initial basic feasible solutions. Okay, and see here the basis, in the basis the quantities, that is a1 and a2 form the basis. So here we write a1 and a2, and here we write the basic variables are corresponding to a1 and a2, that is x1 and x2. Okay, and here we write the cost corresponding to x1 and x2, that is cost corresponding to x1 and x2 from the objective function, that is this is the coefficient corresponding to x1 and this is the coefficient corresponding to x2, that is 2 and 1. Here clear, I think this is the clear. So 2 and 1 the cost for the basic variables. Okay, and x1 and x2 are the basic variables and a1 and a2 are the basic vectors. Okay, and the remaining are the non-basic vectors, and x3 and x4 in this case are the non-basic variables. Okay, so this is clear, I think. And if we write in this zj minus cj, so how we calculate the zj minus cj? This into this plus this into this minus this. Okay, that is what we just write. So 1 into 0 plus 1 into 2, that is 2 minus 2, this gives 0, and we don't need to calculate corresponding to the basic value of zj minus cj corresponding to the basic vectors. Okay, so these terms, that is zj minus cj term corresponding to the basic vectors or basic variables must be 0. Okay, since a1 and a2 are the basic vectors, that is x1 and x2 are forms the basis, that means corresponding to a1 and a2 zj minus cj value is 0, must be 0. Okay, now we have calculated the zj minus cj, that is z3 minus c3 corresponding to a3, basic vectors a3, that is minus 1 into 1 plus 0 into 2. Okay, plus 0 into 2, this into this plus this into this minus this. Okay, so 1 into minus 1 minus 1 minus, yet this is 0 minus 2, that is minus 1 minus 2 gives minus 3. Okay, and similarly 1 into this plus 2 into this 4. Okay, but 1 into 1 means 1 minus 2 into 2 4. So 1 into 1 plus 4 5 minus 9, 5 minus 9 gives minus 4. Okay, so these are the terms. Now here we observe that z3 minus c3 term is negative. Okay, so this is term is negative, and y13 and y23 are not positive. This is negative also, are not positive. Okay, are not positive. These two terms are y, this is y13 and this is y23, that is 0, y13 this is equal to 0 and y23 is equal to minus 1. Therefore y13 and y23 are not positive term. Therefore by this above theorem yij less equal to 0 for all I. Okay, so this is satisfied. That means what? That means the LPP has unbounded solution. Okay, so this is the theorem and this is the example based on the theorem, and this is the simplex algorithm. Okay, and in this case optimality conditions zj minus cj what, satisfied or not? This is not satisfied. That means in this case the optimal solution, that is the LPP has no solution, or you can say unbounded solution. Okay, so this is the theorem and this is the example. Now we comes to another example theorem, so which is optimal alternative optimal solution, that is more than one solution. Okay, so the theorem says that if an optimal stage of the simplex algorithm zj minus cj greater or equal to 0 for some non-basic vector aj with yij greater than 0 for at least one I, then there are at most there are more than one optimal solution. What we can say? Zj minus Cj equal to 0 for some non-basic vector aj with yij greater than 0. That means what? That means this here a3 and a4 are the non-basic vectors. If z3 minus c3 equal to 0 in this case, then as for corresponding to the non-basic vector a3, then we say that the LPP has more than one solution. Okay, so let us take an example for this type of problems. Consider maximum of z equal to 2x1 plus 5x2, this one subject to these two constant xi greater or equal to 0 is non-negative. Now we write first see 0 the corresponding what basic vectors, corresponding vectors are a1, a2, a3 and a4. Okay, so see here if we write the coefficient of this A matrix, that is coefficient matrix, then we get 0, 1, 2, 3 for the first case, and 1, 0, minus 4, minus 2 for the second constant, and the value of B is 4 and 3. This is the basis vector. Okay, sorry, this is the vectors, and the basis vectors, how we write the basic vectors and how we choose the initial basic feasible solutions. Okay, so see here a2 and a1 form the basis. Since 1, 0, 0, 1 is a unit vector or unit matrix corresponding to this a2 and a1, that means we say that a2 and a1 form the basis. Here first we write a2, then we write a1, that is a2 and a1 from the unit basis vector. Okay, so here we write the cost corresponding to a2 and a1, the cost corresponding to a2 is 5 and the cost corresponding to a1 is 1. Okay, and the basic variables corresponding to the vectors x2 and x1. Okay, so this is the table, and 3 and 4 is the for the corresponding a2 and a1, that is this is and this one. So 3 and 4, 3, 4, a2, a1, 0, 0 is the initial basic feasible solution. Okay, in the above problem we choose a1, a2, 0, 0, that since a1 and a2 form the basis, and in this case since a2 and a1 form the basis, therefore we write a2 first, then a1, and then the remaining terms are 0 as the initial basic feasible solutions. Okay, I think you are understand this thing, how we write these tables and how we take the initial basic feasible solutions. Okay, now we calculate the zj minus cj term. So corresponding to the unit vectors, that is these are, since these two vectors are in the basis, therefore j minus cj term corresponding to these two vectors are 0. We don't need to calculate these terms. Now we calculate for a3. So a3 means what? A3 means z3 minus c3. So 4 into 2 plus 2 into 5 minus 2. Okay, so minus 4 into 2 plus 2 into 5 minus 5. But this gives what? This gives minus 8 plus 10 minus 5. Okay, so this gives, I think we made a mistake, I think. Okay, minus 8 plus 10 minus 2 minus 2. Okay, minus 8 plus 10 minus 2. So this is equal to 0. Therefore z3 minus c3 is 0 corresponding to the non-basic variable a3. Okay, so for this the theorem says that if the non-basic variables are 0 corresponding to the non-basic vector aj and yij greater than 0 for at least one I. See here y13 means what? y13 equal to 2, which is greater than 0. Therefore we get at least one yi3 which is greater than 0. We don't need to check whether these two, since this is since this is negative also, but we need at least one yi3. Okay, so for y13 equal to 2 which is greater than 0, therefore the this result, that is this theorem holds. From this theorem we can say that the LPP has multiple optimal solutions. Okay, so and since this is the zj minus cj term is greater or equal to 0, that means this is an optimality condition satisfies, therefore this is an optimal solution. And how we write the optimal solution? These are the solutions. Okay, so x2 equal to 4 and x1 equal to 3 and remaining vectors are 0, that is x1 equal to 3, x2 equal to 4 and x3 equal to 0 and x4 equal to 0 gives the what? Gives the optimal solution. And max z equal to, we just put the values of x1, x2, x3 and x4, we get 26 is the optimal solution, that is maximum value of z equal to 26. Okay, but we have z3 minus c3 equal to 0 corresponding to a non-basic vector a3 and y13 this is greater than 0. I already say this. So thus the solution is not unique. To obtain the alternative solution, choose a3 as the incoming vector for the outgoing vector we select. So this is the incoming vector. What incoming vector is a3. Okay, and for I just say above that we will choose the y minimum term of this one. So we calculate this for to select the outgoing vector. Okay, which the the minimum value for this x bi by yi3 for yi3 greater than 0. The minimum most gives the outgoing vector. Okay, so here we get 4 by 2, that is yi3 means what, this one, so this, and x bi means this one. Okay, so 4 by 2 and 3 by minus 2, therefore we avoid this, just we write 4 by 2, that is only one thing, therefore a what, that is a, this a2, this a2 is the outgoing vector and a3 is the incoming vector. Okay, so we write here a3, okay, instead of a2, because a2 leave the basis and a3 incoming to the basis. Okay, so this is the thing which is happening here. So see, then what, we write the cost corresponding to a3. So corresponding cost corresponding to a3 is 2 here, and the basic variable corresponding to a3 is x3 here. Okay, now our work is what, this is the key element. Okay, since this is y3 is the minimum element, this element is the minimum, this is the element for which x bi, this element is minimum, this is the element for which x bi by yi3 is minimum, therefore this element is said to be the key element. Okay, this element is key element, and we have to what, we have to change this key element to the identity element, that is all the elements are divided by 2 for to get this element to be 1. Okay, so we do this here, this is 4, so 2 0 half and 3 by 2, we just divide the elements of the first row, okay, from here to here by 2 to get this element is unit. Okay, and now see that a3 and a1 forms the basis, 1 0 0 1, this forms the basis, therefore and the remaining work is, see, this is we hold this element, and what, there are operations, but the shortest trick is to find the another elements, this into this, okay, minus this into this element divided by this element 2. Okay, so to get this element. Okay, so starting from this 2, the 2 into 3 gives 6, minus this 4 into minus 4 gives 16, so 6 plus 16 gives 22 divided by these 2, and remaining the other elements we comes as with this same operation. Okay, so this is the operation we apply here. Here you can take another operation which write in the books, that is R2 minus 4 R1 types, this type of relations, you can take this type of relations also, but here we calculate the LPB terms by this calculation. Okay, if you are not understanding this calculation, then you can just write by the row operation. Okay, elementary row operation. Okay, you can just do this by elementary row operations. Okay, so we get this element is 11, this element must be 1 because this forms the basis. Now for this element we just write here from here this 2 into 0, okay, minus this into this, that is 4, so 4 by 2, this gives, these elements comes 2. Okay, see, this element comes 2, this is 0, and for these elements the same operation holds. Okay, so 2 into 2 minus this into this, sorry, 4 plus 3 into 4 gives what, 3 into 4 means 12, 4 plus 12 means 16 by 2, that is 8. Okay, so this is the 8. Now the same case to calculate zj minus c, since these and these are forms the basis, so these two terms are 0, and then this into this plus this into this minus this gives 0, and similarly this 8 into 2 plus 3 by 2 into 2 minus 1, this gives 18. Okay, so zj minus cj greater equal to 0 again satisfies, that means the optimal condition, optimality condition satisfied. Okay, so that means the answer is what, these are the answers. So x1 is 11 and x3 is 12 and remaining are 0. So x1 is 11, x2 0, x3 2 and x4 is equal to 0. This gives the another optimal solution, and maximum value of this z are same, that is 26 in this case also. Okay, so if you not understanding this calculation, okay, comment me in the comment section below. Just take the key element and starting from the key element you go corresponding. If suppose if we find this element, so this into this minus this element into this element by this element, key element. Okay, if we write this element, so we need just this element and this element. So from starting from key element, this into this minus this into this by key element. Okay, this is the calculation. Okay, you don't need to write any elementary row operation. Okay, this is the shortcut calculation. Now we write a flowchart here to understanding the, just a minute, to understanding what, to understanding the simplex method. Okay, so first we have to write the LPP in the standard form, then determine IBFS, this is the second work. Compute the net evaluation, that is first we write the tables, and net evaluation means Zj minus Cj. If there is any negative net evaluation, that means what, Zj minus Cj is less than 0, this is called the net evaluation. Okay, so if is no, that is optimal condition satisfied, that means Zj minus Cj is greater or equal to 0, that is optimality condition satisfied. If yes, that is Zj minus Cj is less than 0, then is there any column with negative net evaluation whose all components are less equal to 0? If yes, then this has unbounded solution. We discussed it above. Okay, if there is no, that is there is no even net evaluation whose all components less equal to 0, then choose the most negative evaluation corresponding to the non-basic vectors enters the basis. Okay, that is for case of in this case, if there are no negative components evaluation, so choose the most negative net evaluation, that is Zj minus Cj is the most negative, choose, and this enters corresponding to the this net evaluation, the basic vector enters the basis. Okay, select the positive components of the incoming vector and divide the corresponding basis variable by them. Okay, choose the smallest ratio, that is what, minimum of the smallest ratio of the basis vector, that is x bi, by corresponding to the mean ratio, that is y, I think I j. Okay, the for corresponding the vectors. Okay, to leave the basis. Okay, for which this is minimum, the vectors leave the basis. Set up the new simplex table and necessary computation, the computation we will say, and compute the net evaluation. Then also this process is followed. Okay, so up to we check the optimality condition is satisfied, up to that part, or up to that the simplex method continuing. Okay, so this is the lecture. I think this simplex method is a little tough to understanding, but I recommend you that whether you which book you read in the BSc. Okay, so just go through the simplex algorithm once. Okay, and attend this lecture. I think this will be very helpful for you. Okay, so if the video is helpful and if there is any confusion, then please comment me in the comment section below, and like the video if possible, and subscribe the channel. Okay, so thank you, see you again in the next video.